AP style FRQ questions are quite challenging. I'm going to go through the following sample question with you and then leave you to complete some on your own. Water is added to 4.267 grams of UF6. The only products are 3.730 grams of a solid containing only uranium, oxygen, and fluorine, and 0.970 grams of a gas. The gas is 95% fluorine and the remainder is hydrogen. The first thing you want to do every single time is write out the chemical reaction that you believe is occurring. So I have water being added to UF6. So my reactants are UF6 and H2O. And products are this solid containing uranium, oxygen, and fluorine. We don't know the subscripts. And a gas that's 95% fluorine and the remainder is hydrogen. So I'm going to put those in the correct order. Hydrogen first, fluorine second because it's the most electronegative. We also want to include our starting amounts. 4.267 grams of UF6. There's 3.730 grams of our solid and 0.970 grams of that gas. So part A says, from these data, determine the empirical formula of the gas. I'm going to start here. A. So think back to Chem 1. What is an empirical formula? The lowest ratio of moles to moles of elements in a formula. So we had a little rhyme that we use: percent to mass, mass to mole, divide by small, multiply till whole. And we're going to do that for step 1 or for part A. We have 95% fluorine and the remaining is oxygen. So I'm going to take that 95%, percent to mass, 95 grams, mass to moles. So in order to go from grams to moles, I need to divide by molar mass. I'm going to do the long method here first, and then I'm going to do the short method the second time around. Molar mass of fluorine is 19 grams. Remember, we always round to the hundredths place. And that's equal to 1 mole of fluorine. Type it into my calculator, 95 divided by 19, and I get 5 moles of fluorine. I'm going to do the same thing with my hydrogen. If it's 95% fluorine and the remaining is hydrogen, that means that 5% is hydrogen. Percent to mass, so there's my mass. Mass to mole. If I have 5 grams of hydrogen and I want to convert it to moles of hydrogen, I'm going to divide by its molar mass, 1.01 grams. And 5 divided by 1.01, let's call that 5. Okay, so percent to mass, mass to mole, divide by small. Well, the smallest number of moles is 5, so it looks like it's a 1-to-1 ratio. I'm going to divide by small, divide by small. And this is a 1, and this is a 1. My numbers are whole, so I don't need to multiply. And my empirical formula is for every 1 hydrogen, I have a 1 fluorine. Part B, what fraction of the fluorine of the original compound is in the solid and what fraction is in the gas after the reaction? Remember that a fraction is nothing more than part divided by whole. So the part that we want to find is the amount of fluorine in the solid and also in the gas, and our whole is the amount of fluorine that there is in the original compound. So for part B, let's start by finding the whole. How much fluorine is in the original compound? If I look up here, it looks like I have 4.267 grams of this solid UF6. I can take the mass of the entire solid, and using some stoichiometry, I can figure out the moles of fluorine, and I can also figure out grams of fluorine. in this compound. Because I see that my amounts of fluorine over on the right hand side are also in grams, we're going to go all the way to grams instead of stopping at moles. So let's give part B a try. B. I'm going to start with that 4.267 grams of UF6. And I'm going to use some stoichiometry to get all the way to grams of fluorine. So molar mass of UF6, I calculated it earlier, 1 uranium and 6 fluorine, is a grand total of 352.03 grams. That's equal to 1 mole of UF6. Remember that our ultimate goal is to find grams of UF6. There is an alternate way you can solve this problem by going to moles, but I'm going to go all the way to grams. So I need to get rid of those moles of UF6. So for every 1 mole of UF6, there are 6 moles of fluorine, and 1 mole of fluorine is equal to 19 grams. Got a little messy there at the end, but hopefully you get the drift. Punch that into your calculator, and I've got 1, 2, 3, 4 significant figures. So the number of grams of fluorine in my original compound, the whole, is 1.382 grams of fluorine. So I have my whole. What I need to complete part B is the part. So I need what part is in the solid and what part is in the gas on the product side. So let's take a look at our products. We have this solid UOF, but what we don't know about that solid are the subscripts or the molar ratios. I'm sure I'm going to have to figure that out later on in the problem. So what I can't do is use that 3.730 grams of the solid to figure out the number of moles or number of grams of that fluorine, because I don't know what the molar ratio is between the U, the O, and the F. That means I have to start with my gas, the HF, and I'm going to convert 0.970 grams of HF to grams of just fluorine, so I can do my part divided by whole. You have two options. You can use stoichiometry just like we did up here in this problem to solve for number of grams of fluorine in this hydrofluoric acid in this HF. But if I look at the problem up here, it told me that it's 95% fluorine, and that's 95% fluorine by mass. So I'm going to do a little shortcut here, and I'm going to take the total mass of that gas, 0.970, and I'm going to multiply it by that 95%, 0.95, and that's going to give me the total mass of fluorine in my sample. Total mass is 0.9215 if I use my significant figures. 9215 grams of fluorine. And this is the total number of grams of fluorine in the gas. So I'm going to put gas here just so I know who's who. And now I can answer part B. What fraction of fluorine of the original compound is in the solid? What fraction is in the gas? I can answer the last part. What part is in the gas? So my fraction is part divided by whole. My part is here, 0.9215 grams of fluorine in the gas divided by whole. Number of grams of fluorine in my original compound up here was 1.382 grams of fluorine. I'm going to put original here. And it doesn't ask me for a percent, so I'm not going to multiply by 100. I'm simply going to divide, and if I round, I get 0.67. And this is a fraction of fluorine that's in the gas. So again, I'm going to put GAS, gas, next to it so I know what I'm working with. So if there is 0.67, and that's my worked out fraction of fluorine in the gas. That means the remainder has to be in the solid itself. So this fraction, of course, is out of 1. So I'm going to 1 minus 0.67, and that means the remainder, 0.33, must be the fraction of fluorine in my solid on the product side. So I've got two answers here. I guess I should have put them side by side, but here's one answer and here's the other. The other option would be to take all of your answers to moles instead of grams of fluorine, and you do the same process, part divided by whole, and you should get the same correct answer. Okay, here comes the fun part, part C. What is the formula of the solid product? If I want to find the formula, that means I need my lowest ratio of moles to moles for this UOF solid product that I've made over on the right-hand side. Before we do that, I want you to think about the law of conservation of mass. Law of conservation of mass says that the mass on the left is equal to the mass on the right. The number of moles of uranium in the reactants is equal to the number of moles of uranium on the product side. The number of moles of hydrogen on my reactant side is equal to number of moles or number of grams. It doesn't matter because they're going to be equal on the product side. So whatever's on the left is equal to what's on the right in terms of mass and in terms of moles. So, and the information that we've already solved in part A and part B to figure out our moles of uranium, oxygen, and fluorine and create our. So part C, here we go. I need to find the number of moles of uranium, oxygen, and fluorine in this compound over here on the end. My arrow didn't come up. There we go. I need to find number of moles of each one of those elements. Now remember law of conservation of mass, the number of moles of uranium on the left, which all moles are going to be in this one reactant. That's great news for me. So moles of uranium in this U of 6 is going to be equal to moles of uranium in this product over here. So let's take the information that we already know about UF6. I know that of the 4.267 grams of UF6, that 1.382 grams of that is fluorine. So let's use that information and let's find the remaining balance. If I subtract 4.267 grams of UF6, and if I subtract 1.382 grams of fluorine, the remaining balance is going to give me grams of uranium. I got 2.885 grams of uranium, and guess what we can do with those grams of uranium? Always go back to base, and our base is a mole. So 2.885 grams of uranium. If I want to convert grams of uranium to moles of uranium, I'm going to divide by molar mass of uranium, which is 238.03, and I get 0.01212 moles uranium. To complete my formula, I still need moles of oxygen and moles of fluorine. I can solve for moles of oxygen. It's going to be a little bit of a doozy because I'm going to have to, first of all, use the law of conservation of mass and figure out what is the total mass I have over here on the product side. I know total mass of products should equal total mass of the reactants. So I would take this 4.267 and subtract this total mass over here on the product side. That will give me mass of the H2O. And I can take the mass of the H2O and convert it to moles of oxygen or grams of oxygen. That's kind of a lengthy process. And here's a clue. If you've already done some math in the previous portions of a free response question, you're going to use them in the rest of your problem. Here, I solved for the fraction of fluorine in my solid, and I'm going to use that to determine the number of grams of fluorine that I have in this UOF compound. I'm running out of space, so I squished everything up there. All right, so now let's find our moles of fluorine. How did we get that 0.33, or what does that mean? That is my fraction of fluorine in the solid. Fraction meaning part out of the whole. So the part, that number of grams, is what I'm looking for. So my part is the X. The whole, what was the total number of grams of fluorine? I had it up here, 1.382 grams of fluorine. And we said that fraction was equal to 0.33. And why did I do that? I did that to show you that if I want to find the number of grams, the part of fluorine in my solid, I'm going to take this 1.382, I'm going to multiply it by 0.33, and that's going to give me the number of grams of fluorine in my product. So punch that into your calculator, and I get 0.4561. 4561 grams of fluorine. But we want to create a formula. I already have my moles of uranium, so I need moles of fluorine. To go from grams of fluorine to moles of fluorine, I'm going to divide by molar mass of fluorine, which is 19 grams. And that gives me same number of significant figures, 0.02400 moles of fluorine. So I've got 2 parts done. The last thing I have to do is find number of moles of oxygen. Let's analyze what we know so far. I know that I have a solid product with uranium, oxygen, and fluorine. I know the total mass of that product is 3.730 grams. Out of that total number of grams, I know the number of grams that come from uranium, and I know the number of grams that come from fluorine. I'm going to use that information to solve for remaining grams. That will give me grams of oxygen, and I can go from grams of oxygen to moles of oxygen, and then I can find the formula of my compound. So let's start there. 3.730 grams of UOF. I'm going to subtract the grams of uranium minus 2.885 grams of uranium. I'm going to subtract the grams of fluorine minus 0.4561 grams of fluorine, and the remainder is going to be grams of oxygen. So I typed that in, and I got 0.3889. If I round using significant figures, that's 0.3, it's 3 places to the right, 389 grams of oxygen. I don't want grams of oxygen, I want moles of oxygen, so I'm going to divide by its molar mass. Molar mass of oxygen is 16 grams. That's going to give me 0.0243 moles of oxygen. And now we're ready to find our formula. So the formula is going to be the lowest ratio of moles to moles to moles of uranium to oxygen to fluorine. So I already have my moles. I've got 0.01212 moles of uranium, I have 0.024 moles of fluorine, and 0.0243 moles of oxygen. Most of you will probably already see what the ratio is, but for those of you who are still struggling, we're going to divide by the smallest number of moles, which is a 0.1212. So I'm going to divide by 0.01212, and that gives me the number 1. I'm going to divide this by 0.01212, and 0.024 divided by 0.012, that gives me 2. And the same thing here, 0.01212, and that should give me 2. So that means for every 1 mole of uranium, I have 2 moles of oxygen and 2 moles of fluorine. So here is my formula for the solid product. And the last part asks us to find or to balance the equation between UF6 and H2O, and we're going to assume that the empirical formula of this gas that we found up here, part A, this HF, the empirical formula is the true formula for that gas. So UF6 plus H2O, and then we found our formula to be UO2F2 plus HF. So we're going to balance our formula here. Our uraniums look balanced. Our fluorine, I have 2, 3 fluorine. Hydrogens, I have 2 here, 1 there. Oxygen, 2 and 1. So if we put, let me choose a different color. If I put a 2 in front, that's 2 uranium, 2 uranium. That gives me 4 oxygen. I need to put a 2 there. Oh, not a 2, a 4. Get rid of that, and let's put a 4. 4 oxygen, 4 oxygen. I have 12 fluorine, 4 fluorine over here on this side. That means I need 8 more. And I have 8 hydrogen, 8 hydrogen. Looks like I'm balanced. As you can see, a ton of math. It's all over the place, but none of the math was too complex that you couldn't answer it. None of the math was any different than what we did in pre-AP Chem or Chem 1. What you have to do is use logic and kind of problem solving to use those concepts that you learned in Chem 1 and apply them to this long, drawn out question. A tip that I want you to remember is that if you've done some math in a part A or part B of a problem, bank on using it in the remainder of the problem. So if I did something in part A, I'm probably going to use it in part B or C, etc., etc.